So welcome. Let me just get my pen going here, which is this plugged in. Let me get my pen going here, and we will get started on this, the second segment of our notes. We have 4 chapters on electricity, electrostatics, that kind of thing. Let me go down here. Let's do a red pen. So basically, electric field notes. Electric field, that's an interesting thing. Why are we talking electric field? Although electric field is not a very obvious thing, it's a really useful way of thinking about things. Let's start at the beginning, and let's start about just discovery of electricity. And people realized there was this strange physical phenomenon when they'd basically accidentally rub different materials together. Fur is something which is very useful in electrostatics, and there's also different types of things like ebony, different types of plastics they didn't have back in the day, but they had other insulating rods. And if you rub these things together, then there's a tendency for some things to give up electrons very easily, and for other things to want electrons. And if that happens, then the object which gives up electrons easily becomes positively charged, and the thing that likes to get electrons becomes negatively charged. So there's still, in the two objects, there's still the same amount of positive and negative charges. So the two objects as a whole are neutral, but one of them has become positively charged and the other has become negatively charged. And the thing that the electric thing is that opposite charges attract. So what did the ancients see? They just saw that these things, sometimes when you rub them, they pull together. Okay, there was this force, who knows what it was, and they started exploring it. And bit by bit, over a long time, they learned more and more about this phenomenon. And then round about the 1890s, into the 1900s, they were playing with these phenomena. They'd learned by that time, I guess Benjamin Franklin had learned that lightning was a part of this family, part of this electrical phenomenon. And they'd learned how to use chemistry to store this electrical phenomenon. And they'd even learned how to make called lightning jars, which basically enabled you to store charge. And it wasn't all that useful. It was kind of like they didn't have much they could do with these things. It was just there. It was kind of like almost like a magic show to some extent. Then they started playing with vacuums and electrical high voltages. And they started seeing weird phenomenon like the glow inside a vacuum chamber when you have a high voltage discharge inside. And that glow can be pushed around by a magnetic field. So there was a whole exploration of this phenomenon. And they came up with the overall picture, which is that there are positive and negative charges. And the atoms are made up of electrons, which are negatively charged, and protons, which are positively charged. And that in most materials, these things are, certainly in atoms, these things are balancing. So there's the same amount of positive charge as there is a negative charge. Because the electrons are whizzing around at the outside of the atom, they can be removed or maybe added. So you can change the balance of the atom by moving electrons around. And if you can get these electrons to flow from one plate of an electrochemical battery to another plate of electrochemical battery, you can actually get a current flowing. And this current will shock you sometimes, or maybe it can cause some changes. Maybe it'll cause a piece of wire to glow if there's enough of it. So there's the beginning of current power production, if you like. One of the key things in this was good old Millikan. Millikan was, so you can argue this in many ways. Benjamin Franklin was really quite an amazing person. and he did a whole bunch of things, some of which were scientific. So Benjamin Franklin deserves his place in the Hall of Fame for Science. But frankly, in his day, most of the science was being done in Europe. I mean, just more stable communities, more science, more of a tradition, etc., etc., etc. And really, Millikan was an American scientist who was one of the first scientists from America to do something where the world paid attention, where it was like, whoa, that was good, you know. And quickly followed where a lot of people in America were doing stuff where people said that's good, but he was one of the first people. And what he did was, we knew that there were positive and negative charges, and what he did was very clever. He wanted to find the charge, the amount of charge in a charge. It sounds weird, but it's like, when you think about things from a fundamental level, there's this idea that, well, what's the smallest bit of it that you can get? And often the smallest bit is so small nobody cares about. What's the smallest amount of water you can get? You know, I mean, who cares really to some extent? What Millikan did was he wanted to know what was the smallest amount of charge he could get, and he came up with a very clever way of doing it. He basically took oil, sewing machine oil, very light oil, not like oil you oil your bike with or oil you put in your car. It was very light oil, and he had it in a bottle basically, and he imagines using a perfume spray. He sprayed out some of the oil, and just the force of friction actually can cause some of these things to get charged. In a more modern version, they'll also use a radioactive source actually just to cause some ionization. But just the force of friction, the act of the oil droplet rubbing against the side of this nozzle will cause some ionization, some positive atom, some positive droplets, some negative droplets. And they are so small that they quickly reach their terminal velocity. Remember that the smaller something is, the slower its terminal velocity. If you don't do this, but if you drop a mouse off a building, the chances are it will just land and scamper away, because it very quickly reached its terminal velocity, and so its collision velocity was not that high. Whereas if you take, a person and throw them off the same building, their terminal velocity is much faster. So for them, the change of momentum when they land is much greater, so the force on them is much greater. So these things quickly reach their terminal velocity, and what that means is they're not accelerating noticeably. They're basically traveling at constant velocity, and that's beautiful because it makes the math analysis quite kind of easy. So he sprays them into this upper chamber, and they go into space, and then they just start falling, drifting, if you like, downwards, quite slowly. And so he put a floor in with a hole, and so he has one, if you like, now we're in the bottom room, and there's a hole in the ceiling, and these charged particles and uncharged particles are falling through the ceiling. He illuminates them with a light, and he uses some kind of microscope to look at the illumination. He has a little reticule, it's called, a little grid system in the actual eyepiece of the microscope, so we can count how long it takes to go a certain really angular distance, but you can think of it as a certain distance up and down the chamber. And he put a plate on the top and a plate on the bottom and a power supply, so you can make this top plate positive and the bottom plate negative, or you can make the top plate negative and the bottom plate positive, so you can have electric field going up, electric field going down, or no electric field. And then you can look at the effect on these things. And what you basically do in the experiment is you pick a particular droplet which has charge. How do you know it has charge? When you put the voltage on it, it slows down or it speeds up or whatever. And then you just drive it upwards and downwards, and you time it. So you're picking this one particle and you're timing it as it goes backwards and forwards, like running an obstacle course. the bigger it is, the slower it moves, the smaller it is, the faster it moves, and so on. And if you do one of them, you can eventually figure out its charge. And you go, what to do? Doesn't tell you much. Because the next droplet has a different amount of charge, and the next droplet has a different amount of charge, and the next droplet has a different amount of charge. It's haphazard how much charge they have. And so and pretty well everybody who does physics does this experiment. It's like a rite of passage. You spend either 4 hours or 8 hours in a room with no windows doing this experiment. You look at, if you can, tens or maybe even, 100 droplets to try and get good statistics. And what you find is if this is charge here, and this is like your distribution of droplets, you might find you had 3 droplets were at that charge, and you get 2 droplets here, and you get maybe 7 droplets, I can't draw it, but maybe 4 droplets there, and you go on and you do like as many of these as you can, and what you realize is that there's a whole wide spread of possible amounts of charge. So at first it might seem hopeless, but then you realize, what really counts, the really instructive thing, is not what any one droplet has, but the smallest difference in the charge between droplets. That's what really counts. If your cars are made so that they can only do a whole number of miles per hour, and I'm doing 35 and you're doing 37, and somebody else is doing 42, and somebody else is doing 46, and somebody else is doing 36, you look and look and look, and you'll find that eventually you'll get gaps. And the smallest gap you can find is 1 mile an hour, and there's never any half miles an hour. You get plenty of 2s and plenty of 5s, but nothing less than 1. And you can double the number of experiments, and you still get nothing less than 1 mile an hour gap. That tells you, it goes in whole number of miles per hour. Did the same thing with this. They looked and said, let's have a look at these difference in charges, and they got a whole variety of charges, but the more and more charges that you look at, the more you find that the smallest gap is 1.6 times 10 to the minus 19 coulombs. And so they say, okay, that's the smallest charge you can have. That's the smallest charge. And that turns out to be the charge of a proton or the charge of an electron. Okay. So, and you realize the trick with this experiment is you do a lot of particles. You don't spend time trying to get one particle perfectly. It won't tell you anything. You've got to do a lot of particles because you're looking for the gaps between the values. I have a little video here. I'd forgotten about this. I have a little video. Have we got sound today?
In 1909, Yes. Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
Cool. So there we have it. Let's have a look. Okay, so good old Millikan found there was a smallest amount of charge of the electron. We can make charges by abrasion. We get 2 different types of material. So there's all this folklore about which materials you use. There's various combinations: glass rods, ebonite rods, rabbit fur, silk. We come across static cling when your socks stick to your shirts. Then that's what's going on. The abrasion has caused this thing. If you're in the north on a cold winter's day and you walk across a carpeted floor and you put your finger out to touch the door handle, you get quite a noticeable shock because your shoes have been rubbing on the carpet and there's been a buildup of electrons. And when you have a lot of electrons and the door handle doesn't, it's going to jump from you to the door handle, and you feel that change. So basically, we'd like to do some experiments where we look at these charges and see what they can do. And so we have a method of charging, which is basically taking a cloth and taking a rod and rubbing one against the other and trying to build up some charge. It's really haphazard. It's like trying to butter bread when you're blindfolded. You kind of know how to do it, but it's kind of like you're not really precise. Somewhere on that rod, there's some charges, and then you've got to do something with it. And typically, we'll try to put it onto some kind of thing that will show the effect. And a common thing is we could put it on an insulator. So we take something like a polystyrene cup or something. And we take our rod, which has these charges on it, and we have an insulator that's got no charges on to begin with, and we rub our charges onto the insulator. And again, maybe they come off at this point, and maybe they'll come off at that point. Who knows? The thing about an insulator, the reason why it's an insulator is that it does not let charges flow. By definition, that's an insulator. And so you tend to get the charges where you happen to lay them, and they stay there. Now, these charges are invisible to the eye, but you can see the effect. So now we have an object which has charges in one locality, but not in other localities. And so the behavior of the object is not particularly obvious. You might look at the region close to where the charges are and see a strong electrostatic charge, or you might look at the other side and not see much of an electrostatic charge. So people often complain in electrostatics about the repeatability of the experiments. Are like, man, this I can kind of see what's going on, but I showed it to my buddy and they couldn't see anything, and now I can see it, and etc. That's part of the issue. What we can do to make life a bit better is we can say, let's give up on an insulator. Let's have a isolated conductor. So now we have a metal ball on top of an insulating stand. We don't want the metal ball connected to ground because ground is effectively a sink for charge carriers. They all want to go to ground because it's such a the earth is so big, they'll find a home somewhere there. So they all want to go to ground. They want to get away from each other. That's the driving force. There's a whole bunch of charges on a rod. They're all similar charges. They don't want to be around each other. So they'll do anything to get away from each other. Okay, they'd like to get away from each other. We rub on this isolated conductor, and some of them come off. And here's the beautiful thing about the isolated conductor. Once we take the rod away, then these guys, they just separate as much as they can. So they spread themselves out evenly. It would really form a tetrahedron, but I've shown it in 2 dimensions like this. And basically, they're just as far away from each other as they can. The field is uniform around this thing. It's highly repeatable. It's kind of nice. So we tend to use isolated conductors for these kind of experiments as often as we use insulators in these experiments. Yeah. In this case, the isolated conductor is metal, yeah. It could be, for instance, they used to use what they called pith balls, which, as best as I can tell, before plastic, as best as I can tell, they were like it's like organic, it's a bit like the inside of an orange pip. That's about the best I can tell you. When it's plastic or wood or something like that, they stay put. So the idea, an insulator does not allow charges to pass through it or across it, and a conductor does. By the way, so you might turn and say, insulators are a total drag, but here's an interesting thing. So I take charges and I take an insulator. Let's say, oh, I don't know, a piece of paper, and I put the charges down on a pattern. They're not going to move. I then come in with some dried ink and I sprinkle it on the surface. And that little neutral particle, as we'll see in a minute, will tend to stick where the charge is. So now I have ink sticking to this bit. I just blow the rest away. I then, from my chemistry, recognize that that dried ink particle will bond to the fibers of the paper if I heat it. So I run it through a little heating press, and from then on I have a printed page. And that's a photocopier. In essence, that's exactly what a photocopier is. And, you know, if you'd invented that, that would have been, you'd be very rich by now. But this guy called Xerox did it. I don't know. I remember when I started teaching using a Spirit printer, which was precursor to this, and it was a messy process. Getting a worksheet for a class was a messy, wet chemistry process. And then these guys come along, you press a button and it comes out. It's like magic. And it's so, I mean, and I'm the kind of scientist where I'd have said, oh yeah, stay away from insulators. They're so unreliable. And yet engineering is what comes along and makes this process reliable. It's the reason why we have photocopiers is because of engineering, not so much because of physics. It's engineering that makes those things work. And I always tend to underestimate what engineering can do. Yes?
Do you need direct contact to transfer charge?
So, actually, there's another method which we're going to get to, which I skipped for some reason. I have no idea why. Which I will explain to you now, which is called the induction method. And what I do is I have a charged rod, and I have an isolated conductor. An isolated conductor. And what I do is I bring the rod near to the isolated conductor. And so this is neutral, but the electrons can move. So the electrons say, oh, positive charges, let's go to this side. So the electrons tend to congregate on this side. And they left the other side, so we have these 4 exposed protons on the other side, if you like. Yeah, I didn't create these negatives and positives. I took neutrals and just moved the positive, negative, separated them. So now they're relevant. Okay, these negatives want to be near the wand. The positives want to be as far away as they can be. So what I do is, with the wand still in place, the wand still locking these guys together, I touch this and act as a path for ground. These negatives are not going to move because they're held by the wand. These positives want to get far away. They run down my finger, down to ground, and they disappear. So they disappear. I've still got those 4 guys held. There's no question. Those 4 charges still held. I should need to have my eraser out some more. I then break contact with ground. I then remove the rod. I can't draw that. And what happens is that these negatives then spread out. Once that rod is gone, these guys spread out. So I didn't physically touch I did with my finger, but I didn't try and scrape the charges onto the isolated conductor. I used a charging method called induction, which is, in practical terms, much better. That's the way most people do it. Cool. I think what I was trying to do was just plow through this, so I think I took that set of notes out. So let's I should really put it back in because it is valuable. Okay, so we have charges. And we could have two positives, we could have two negatives, we could have a negative and a positive, and we could have a positive and a negative. So we can either have like charges or unlike charges. And in a way, they're a bit like the pull of gravity. What we find is that just as the Earth pulls the moon and the moon pulls the Earth, so a positive charge pulls a negative charge and the negative charge pulls the positive charge. And just like, if you remember good old Newton's law, Fg was equal to big G m1 m2 over d squared or r squared. Isn't this the same equation, just with different symbols? It's the same symmetry, and that's what physics teaches you to look at. It looks for the symmetries. This is a spherically symmetrical system. Why is it spherically symmetrical? Because this electrostatic pull radiates around each of these objects. I think it's best to think in terms of specifically one of the objects being the parent and the other objects being the child. One's the causer and the other one's the affected. Now, in reality, they're both causing and they're both affecting the other one. But if you try and think both things at once, it gets complicated. So I like to think of one as being the Earth and one's been the moon, or one been the sun and one been the Earth, a big one and a little one. So I say here, electrostatic force depends upon the magnitude of each charge. That makes sense. If I had more charge, more pulling or pushing will take place. So the magnitude of each charge and the separation between us, that makes sense also. If the separation did not matter, then a charge on Pluto would affect me as much as a charge that's right next to me. If separation does not matter, then that's the consequence. So I would get static cling on my socks because of a dryer on Pluto. And that makes no sense. It just cannot happen. And even worse, if the separation, if the effect got bigger with separation, then that star in that other galaxy that's 55 light years away would be having an overwhelming effect on me compared with something that's right next to me. So that can't be right. The only real alternative is that, as this separation gets bigger, the effect gets smaller. Then the next question is, how much smaller does it get? And for that, we look at symmetries. What we recognize is that if I imagine one of these charges, there's a thing, a mysterious thing called charge. We don't really understand it. We give it a name. It's like, people call me Tony. Does that specify me? Of course it does not. It's just a label they put on me. Same thing with charge. Do we really understand it? Just ask a whole bunch. Get a younger brother or sister to come into the room. Get that 4-year-old to come into the room and ask Albert Einstein these questions. And they'll have Albert Einstein backed into a corner. Now, he probably will be able to work his way out of it, but a lot of the rest of us will not. Because when you get into these fundamental questions, it's really hard. We can describe the effects because we see the effects. But why is the effect taking place? What is gravity? I struggle with that. It's like, and I think science struggles with that. What is gravity? Maybe some particle physicists have a good answer. Albert Einstein had a space-time answer. It's not easy stuff. So in this case, it's kind of like I think of this thing called charge. And all I can tell you is there's this effect that surrounds it. And it doesn't matter which direction I go in. I can go up and the effect is still there. I can go backwards, forwards. The effect is still there. So I can imagine this sphere of influence. And the key point is it is a sphere of influence. And so I got to take into account the fact that now the effect is spread over a certain size sphere. And now the same effect is spread over a bigger sphere. The area of the influence got greater. So the same amount of stuff was spread thinner and thinner and thinner as I go further away. I can use an analogy. I can take a golf ball, a basketball, a beach ball. I can take a small can of paint and paint on the outside until all the paint is used. Same amount of paint. Cut those things in two. I see a thick layer of paint on the golf ball. I see a thinner layer of paint on the basketball. I see a thin layer of paint on the beach ball. Same amount of stuff got spread out. Or in light, if I take a light bulb and just hold it next to my eye so that I'm on a very small sphere, then very intense. A lot of photons are going into my eyeball. Move it further away, I get less photons going into my eyeball. Whenever I see this spherical symmetry, which occurs with light and gravity and sound and radiation and charge, whenever I see this inverse, this spherical symmetry, I know it's an inverse square law. So that's why these two equations look so similar, because really it's the same physical relationship. It's the same pattern. And if I was to talk about radioactivity, I could get a similar equation. So, okay, so, actually, no, hold on that. It's like, I can get the inverse square law for sure. I'm not sure about the M1 and M2, etc. But, so, all right, I have this equation, and now, if you look in the textbook, it will have a negative sign stuck in here and all this kind of stuff, and it'll have a 1, 2 down here and a 1, 2 down there, and it's like, you know, it's got a definite sign, and I'm not putting the sign in. Why am I not putting the sign in? In fact, I'm telling you even to ignore the sign of the two charges, and the textbook doesn't tell you to ignore the sign of the two charges. Why am I telling you to ignore the sign of the two charges? Because I want to get you away from just learning by rote, this magic formula you turn, and sometimes if you do everything right, well, if you do everything right, it will always give you the right answer, but if you don't do it in quite the right way, you'll get completely the wrong answer. I want you to visualize. Let me give you an example. If you had a positive charge and a positive charge, what sign would F be? Positive or negative force? If you put them both into that equation, if you don't do the absolute values, if you look at the signs, positive 3 for Q, positive 6 for QB, then that's a positive times a positive is a positive. So that would be a positive. If you have a positive times a negative, well, positive times negative is going to give me a negative force, and a negative times a positive is going to be a negative force, but a negative times a negative gives me a positive force. So the sign, if you take into account the sign on the charges, the sign of the force tells you, is it an attractive force or is it a repulsive force? If it's a negative sign on the force, it's attractive. Now, where have we ever used that before? This is a new piece of man-made stuff which is completely arbitrary. And if it's a positive sign on the two charges, it's a repulsive force. This makes no sense. We're just making something up. But that's what that tells you. My advice is forget the positive and the negative. Look at the diagram. If this is a positive and that's a negative, then there'll be an attractive force. So draw it as an attractive force. There's the attractive force. It points from A to B. Now we say, well, hold on. How can I represent this direction of force? Use a vector for it. That's how to do it. Use a vector for it. And so we can say, oh, well, if I just want the magnitude, I don't want the direction, I just take the absolute value of A and multiply it by the absolute value of B, and I divide it by the separation squared, and I use this constant of proportionality in front, this Coulomb's constant, and I get an answer. And the answer is always positive because it's a magnitude. If it's not a magnitude, it's a vector. So then let's do the vector. And the way you do the vector is you say, oh, it's going to be the magnitude multiplied by a unit vector pointing in the right direction. So we go to that next level. We'll do that next. Okay. So what we say is K is a Coulomb's constant. Remember, like Cavendish's constant, G, you know, the universal gravitational constant? So this is the electrostatic equivalent, much bigger number. This is 9 times 10 to the 9. This is a massive effect. If I had every charge in this table every atom in this table being charged, not neutral, I would not be able to raise my hand off it. The electrostatic pull on my hand would polarize my hand so much, it would zap me from a distance. It would be a huge force. And yet, every neutral atom pulls on me, and yet it's very little effect. The gravitational field is so weak, the force is so weak, we need a massive planet just to hold us down, and even then we can jump away from it. So Q is in coulombs, R is in meters. So we say like charges repel, unlike charges attract. So, little story. So electrical engineers tend to talk about Ke as 1 over 4 pi epsilon naught. So they write this equation with 1 over 4 pi epsilon naught in there. So if you pick up some electrical engineering textbooks and you see this equation, it looks very unfamiliar because they're just not using Ke. They're using 1 over 4 pi epsilon naught. In physics, the tradition is we tend to get rid of the epsilon naught and go to the Ke, and it's just our two traditions. You need to know both. We tend to, I'm not gonna, there'll be times when we use both, but it's tradition in physics to use this one slightly and the Ke a lot, yes.
So that's equivalent to 9 times 10 to the 9?
Yes. Yeah, cool. And epsilon naught is called the permittivity of free space. We're going to have the permittivity of free space, and then we're going to have mu naught in magnetism, which is the permeability of free space. So recognize there's going to be something that sounds somewhat similar, which is not the same. Let's do this using a vector. So the thing with a vector is you've got to be careful. Which force are you talking about? This is the force of B on A. So it's the force that A feels because of B. So your language, well, my language matters. I've got to be clear with you about which force I want. And then what I do is I say, well, the force of B on A is equal to Ke QA QB over R squared. That's the magnitude. We've already done that. And the way you get the magnitude to be a vector is you multiply it by a unit vector. So this with a little hat on top, a little roof on top, is a unit vector. It's got a direction, but it's got a magnitude. Its own magnitude is 1. Because if its magnitude was 2, it just doubled the magnitude that I previously worked out. And if its magnitude was 4, I have 4 times the magnitude that I previously worked out. And that can't be, or else I got the wrong answer. So its magnitude is 1. And if it is in the x direction, I can tell you now that will be 1i plus 0j plus 0k. And if it is in the y direction, I can tell you now it will be 0i plus 1j plus 0k. And if it's in the z direction, I can tell you it would be 0i plus 0j plus 1k. If it's in between, then it's going to be some combination of fractions, which when you use Pythagoras's, the square root of x squared plus y squared plus z squared equals 1. So, and I should learn one of these. And I don't. I haven't learned one. So I should go away and learn one of these that would give me, you know, the value of 1. But that's what that unit vector is. It's going to be an ijk vector. So how do we get the ijk vector? Well, we find a vector, or we're given a vector which relates the position of these two guys. That's R with a arrow on top, because it's not a unit vector, but it is a vector. And then we make that into its own unit vector. Let's say I said this was 3i plus 2j plus 1k. Let's say I'm saying that R, that direction vector, the displacement vector from A to B, is 3i plus 2j plus 1k. And I want to now represent this direction, same direction, because it's in the same direction as my force. All these three guys are in the same direction. But I don't want it to be as big as this. How can I change that vector into a unit vector? What do I do?
Divided by the outside body.
Divide it by its own magnitude, yeah? So I divide it by 3 squared plus 2 squared plus 1 squared. That is the unit vector. That is that guy. Okay? So I have a magnitude bit and I have a unit vector bit. Okay? In truth, given two charges, there's, from a teaching point of view or an examining point of view, yes?
So the R square is the magnitude of that vector that you use.
So this 3 squared plus 2 squared plus 1 squared, square root of that is the magnitude of that vector.
So that's R.
So you divide that, you divide the vector r by its own magnitude.
But that's the radius, right?
Which is the rate? Which is,
The square root of.
yes, that would be the numerical value. If you got a ruler, that would be, that guy there is the ruler measurement.
Okay.
It's the magnitude of that separation. Yeah, that's right. Okay. In reality, there's three ways I can ask you this question. Well, two ways really. If that's the force that you want, I could give you that displacement. I could give you that displacement. And I could give you the two displacements for these two from the origin. And if I give you the first one, you simply take that vector 3i plus 2j plus 1k and you divide it by its own magnitude to get the unit vector. 3 squared plus 2 squared plus 1 squared. If I give you the opposite vector, let's say I said, oh yeah, the vector from B to A is minus 3i plus minus 2j plus minus 1k. I gave you the opposite vector. Then you'd say, oh, it's the minus of that. And it's going to be the same thing, isn't it? Minus 2 squared is the same as plus 2 squared. So I just put that negative sign there because it's the opposite direction. Agreed?
Does the minus doesn't show that it's the opposite direction?
So if I give you that vector and you want that unit vector, you got to reverse the signs because it's in the wrong direction, isn't it? It's got the right line, but it's pointing bottom left rather than top right. So that's what that negative sign does.
And what does the -3, -2, and -1 do?
That is that vector. If this vector is plus 3, plus 2, plus 1, then the opposite direction must be minus 3, minus 2, minus 1. If that's positive x, that's minus x. The way you get the opposite vectors, you change the sign on the vector.
Yeah, but it's 2 negative. That's what I was confused.
What's two negatives?
You have 1 in the front of the equation, then you have -3.
Because I'm trying to get the same answer. I'm trying to get that guy.
Oh,
And
okay.
that's pointing in that direction.
I understand.
Yeah, cool. And then the third bit is if I give you the vector to there and the vector to there, you've got to do some vector math. But it's just vectors. So what is the magnitude of the force experienced by a positive 3 coulomb point charge that is located 4 meters from a positive 12 coulomb point charge? So here's positive 3 and here's positive 12. Doesn't matter the direction. All I know is that is 4 meters. And what is the magnitude of the force experienced by the 3 coulomb? I still like to put my arrow in. Fe. There's another arrow there, of course, Fe, but this is the one I'm interested in. I don't care about the direction because I want the magnitude. So I say Fe, mag if you like, is equal to Ke Q1. I like it to forget about the signs, Q2 over R squared. So Fe magnitude is equal to, leave the K in, for at least a little while. And then we'll have, let's have a look, that's going to be 3, and that's going to be 12, and this is going to be 4 squared, which equals 36 KE over 16. So FE over FE mag is equal to 36 over 16, which is, what's that going to be? 2.25? 2.25 KE newtons. Or I can say FE is equal to, what did we say it was? 9 times 10 to the 9 times 2.5 newtons, which equals, sorry, 20.25? Is that right? Oh, 2.25. Yes, 2.25. Sorry, thank you. So what's 9 times 2.25 is going to be 18 and a quarter of 18. A quarter of 9 is 2 and a quarter, so it would be 20 and a quarter.
Yep, 20.25
times 10 to the 9 newtons. Now, frankly, in tests, I've always been a bit worried about how much time you have. I've reduced the number of questions, or at least I've reduced the amount of work. I might have the same number of numerical bits, but there's less to them. So in tests, I will usually say you can leave KE as KE. You can leave mu naught as mu naught. What you can't leave is pies. You've got to work out your pies. And I'd like you, so here's the issue. I'd like you to work out your fractional values. Because what sometimes happens is people leave that as a fraction, and it's right, but then somebody else says it's 16.72 KE, and that's clearly not right. And it's a mistake, and I feel like they can't keep making a mistake. So now I'm worried about their calculator skills. So I've got to then chide them a bit for having a calculator mishap. So then you end up chiding them, and somebody else you're not even chiding because they didn't even attempt the calculator mishap. So I want you to work out, don't leave me fractional things unless I tell you, leave me the fractional things. But you can leave me the KE. Cool. Got to have units on it. So people sometimes think that because I put down KE, I don't need units, but I do need units. What is the magnitude of the force experienced by the 12 Newton charge? Well, only a little space is a kind of dead giveaway that we only need a little bit. And what can you tell me? Can somebody just tell me the answer? It's the same, isn't it? Why is it the same? Whose law are you using? Newton's third law. For every reaction, there's an equal and opposite reaction. The force of the moon on the earth is the same as the force of the earth on the moon. In terms of magnitude, opposite directions, of course, but in terms of magnitude. So is the long version. So let's just do the long version. So a positive 3 coulomb point charge is located at that point. A positive 12 Newton point charge is located at that point. What is the vector force experienced by the 3 coulomb charge? So let's just draw. I'm not going to draw 3 dimensions, but I am going to draw 2 dimensions. And I'm going to put this as plus 3. I'm going to put that as plus 2. Oh, my mistake back here, by the way. Shame on me. Positive 3. Positive 2. It's a repulsive force, isn't it? It didn't matter for the magnitude, but for the vector, it's going to count tremendously. So, shame on me. So I'm going to do that one goes like that, and that one goes like that. Got it?
Yeah. No, I was talking to myself.
Okay, cool. Is this 12? Okay, cool. So now for the 3, this is 2I plus 3J plus 4K meters. glasses on. And for this guy, it's going to be 3I plus 5J plus 1K meters. Now, it's asking me, what is the vector force experienced by the 3 coulomb charge? So there's the vector force. There's the one that I'm interested in. So I am making a command decision here. I got to find a vector representation of the gap between these two charges. And I'm going to find it in that direction. I might as well make my displacement vector the same direction as the force that I'm interested in. Then I don't have to do the double negative thing, you know. Okay. So that's my R. And let's call that, now I'm going to change color pens because I want you to see this clearly, so I'm going to go to black. So I'm going to call this R1. It's a vector. I'm going to call this R2. It's a vector. And I'm going to call this R3. It's a vector. So I'm looking at these arrows, these black arrows. Because I've got to do a bit of vector manipulation here. I want R3. If I think back about my vector diagrams, the process of addition is when you put the tail of the second vector on top of the head of the first vector. So according to this diagram, the black arrows, have I drawn a diagram where I'm adding R3 to R1, or have I drawn a diagram where I'm adding R3 to R2?
You're adding all of it.
It doesn't matter. R3 to R2, right?
I got 3 vectors, R1, R2, R3. Which 2 am I adding together? R2 and R3, because the head of this is connected to the tail of that. That's the process of addition. So the equation for these three the relationship between these 3 vectors is R2 plus R3 is equal to R1. And it's not anything else. Agreed? Everybody comfortable with that? We chose to draw that vector diagram, and it's got a certain relationship, and so I got to know how to look at the diagram and figure out what the relationship is. If I had reversed the direction of R3, if I'd said let R3 go from the 3 positive to the 12 positive, then I would have to change this equation. So now I say, but I want R3, so R3 is equal to R1 minus R2. So R3 is equal to R1 plus minus R2. That makes sense? Let's do IJK. I want to write down R1. R1 we said was 2I, 3J, 4K. I want to subtract from that R2, or I want to add the negative of it. Well, that's going to be minus 3, minus 5, minus 1. I just like to add them together. I don't like doing subtractions. So that's going to be minus 1I, minus 2J, plus 3K. Make sense? So if I change my pens, so I go back to red, I now know, so I go back to red. I now know that that is equal to that. So this equals minus 1I minus 2J plus 3K meters. That's what I know. Okay, what is the vector experienced by the 3 Newton force? Oh, I've got to finish soon. Okay. Let's do this quick as I can. So there's the 3 Newton force. So I say Fe is equal to Ke Q1 Q2 over R squared times R hat. So Fe is equal to Ke. The Q is a 3. The Q2 is a 12. Whoops. The separation is the square root of -1 squared plus -2 squared plus 3 squared. It's just the magnitude of this R3. Agreed? That's the separation. It's the magnitude of that separation. I've got to multiply it by the unit vector. And the unit vector is, well, it's going to be this direction. This is in the right direction. I chose to make it in that direction so it would match up with that. So I go -1i -2j plus 3k over. It's the right direction, but it's too long. It's not a unit vector. Oh, let's make it into a unit vector. I missed something, I know. I'll go back to it in a minute. -1 squared plus -2 squared plus 3 squared. And I made a slip. That square there, I missed. I'm going to pause for a second. So I can neaten this up a little bit. I can say Fe is equal to Ke. If you like, I can go 36 over, and this would be 1 squared plus 4 squared plus 9 squared is going to be 1 plus 4 makes 5 and 9. Is that 14?
Yes.
That's 14. And then that's, no, it's square root and square it, so that's 14. -1i -2j plus 3k over the square root of 14. And if I put in the question, which I will in the test, write me an expression for this is exactly what I want. I'm going to stop there.